Hello everyone, I'm Unsu back from Seoul National University. First, I'd like to thank the organizers for a great benchmark and for the opportunity to present today. This is our second place solution to the RoboSpatial-Home challenge, eliciting special skills from open-weight VLMs zero shot with a per-task recipe. Before I start, a quick confession. I'm not actually a spatial listening researcher. I'm working on adaptive sensing for neural networks. That is, adapting how an agent senses instead of training harder. I joined this challenge to learn the robotics side hands-on. Which spatial problems matter, how models fail, and what transfers. Spoiler, no training was involved. Here's the whole talk on one slide. We had a hard constraint, limited compute, no room to fine-tune anything. So we made a bet. Strong open VLMs already hold more special skill than they show. So we just have to elicit it with inference times choices. That's the recipe. Keep the models fixed, tune the inference per task, and let the model's own reasoning tell us what to choose. No training error, and it worked out 83.1 overall. So this is the setting. One scene, three types of questions, the benchmarks on example. Placing a gray ball in front of a car. Context asked us to point. Compatibility asked whether it fits. Configuration asked whether the relation holds. We get 78.7 on context, 79.1 on compatibility, and 91.5 on configuration. 3 tasks, 3 different skills, and each one ends up needing a different recipe. Our design space is compact, just 6 knobs. The first knob is which model answers. We use 2 open models. Q3VR 32-bit thinking, original.ms think traces. It takes configuration and compatibility. And RoboBrain 2.58V MT, a pointing specialist. It takes context together with QN in a union. The other 5 nodes are or inference time, reasoning on or off, the decoding mode, whether to add a reference frame to the prompt, the parsing, and the point union. And interestingly, the best setting differs by task, sometimes in opposite directions. Greedy wins configurations, sampling wins compatibility, same model, opposite effect. So here's the recipe each task lands on. We will go through them one by one. So starting with configuration, first, what does the default model get wrong? Out of the box, it over-rejects. It keeps saying no to things that are actually true. First one is the monitor behind the sofa. Instead of checking what's behind, it just tells us the monitor is off to the side and rejects to reiterate. And the second one is the microwave above the counter. The microwave is sitting right on the counter, but the model decides on doesn't count as above and rejects again, too strict. Our solution is to tell the model whose perspective to use. We consider 4 types of prompts: default, which says nothing; egocentric, the camera's view; object-centric, the object's own perspective; and word-centric, a God's eye view on fixed word axis. And here's why this matters. The default reads the question literally, but simply naming any frame pushes it into relative spatial reasoning. It even rechecks its answer before committing. The implementation is simple. On the left is the actual prompt, 1 frame instruction, a blank line, then the original question, unchanged. For object-centric, the instruction says to interpret directions from the object's own perspective. On the right, the result. Our choice was object-centric, 88.1 in macro. So a single line of text gave us 6.8 points. Why does it work? These are the same two questions now with the object frame. The sofa trace now anchors the axis. The sofa faces the coffee table, so its back is toward the desk. The monitor is behind it. And the microwave trace gets the relation right. The counter is below the microwave, so yes, it's above. Same model, same questions. The only difference is that this time the perspective is specified. Two smaller choices finish the recipe. First, a consistency fix. Occasionally, the final yes or no token contradicts the model's own reasoning. When that happens, we take the reasoning's conclusion, and on this set, it was right every time. Second, our choice is greedy decoding because sampling reopens over rejections. Here's what changes inside. Three signals. With a frame, traces get about 2.5 times longer on the same token budget. Each frame echoes its own vocabulary back, and planning and decomposition jump from 17 to 95%. The frame doesn't add knowledge, it makes the model listen more. That said, this isn't true perspective taking. The three frames' correct answers overlap heavily, so what matters is having a frame, not which one. The frame triggers spatial reasoning. The model isn't rigorously distinguishing the attribute points, most likely because it was never trained with the viewpoint made explicit. Putting it all together, 81.4 by default plus 6.8 from naming the frame plus 3.4 from the parser, that lands us at 91.5. And a quick check on the right. Balanced accuracy tells the same story. Macro 91.9 right next to the raw score, so the gain is real. 10.2 points without touching a single weight. So there was configuration. Next, compatibility. Does the object fit? One thing about this evaluation set, 83% of the answers are yes, so raw accuracy alone isn't very informative. Selecting a setup on low accuracy would mostly reward that yes bias, and we didn't expect that to generalize. So we compared candidates on balanced accuracy. Instruct is biased the other way, 41.9. Our regional with greedy decoding gets 77.1 raw but catches only half of the no cases, macro 66.4. The fix is again at inference time, switching the decoding to sampling. That's the last row, 79 raw, 74.1 balanced, the setting we submitted. So why does sampling help? Look at the traces. In the headphone example, the answer is no. Greedy answers yes. If we move the mouse pad, it fits. Sampling answers no. The mouse pad is already there, taking the space. In the walks example, the answer is yes. Greedy answers no. Probably too big. Sampling compares actual sizes. About the size of one burner, the freeze top is wider, and answers yes. The pattern, greedy asserts a conclusion, sampling checks the scene. Of course, those were just two examples, so we checked whether the pattern holds across all the traces. We grouped the reasoning into behavior categories. Sampling does about 2.5 times more visualizing and imagining, twice the size reasoning, and twice the space status checking. Greedy does 3.8 times more optimistic assertion and rough eyeballing. One detail worth noting, the weight style hesitation is identical on both sides, 2.13 each, so sampling's advantage comes from grounding, not from hesitating less. So Summing up compatibility, on the balanced side, sampling adds 6 points and the parser adds another 1.7. So 66.4 to 74.1. On the raw side, we land at 79 points, and compared to blindness, we give up a little low accuracy for a much more balanced model. The last one is context, the pointing task. Here the benchmark allows us to 2 points per question, and the answer counts if either one lands inside the target region. The problem, a single model almost always gives just 1 point. RoboBrain 98% of the time, QN 87%, and the 1 point often lands just outside. On the left, below the desk, QN's point falls just outside the mosque. On the right, in front of the kitchen tower, the same thing happens to RoboBrain. The best single model, which is 66.4, so it misses about the third of the questions, while half of the 2-point budget goes unused. So we use that budget. We submit both points, one from each model. The members come from a sweep. Step 1, each model's best settings, and the 2 prepare opposite ones. RoboBrain greedy with no frame, QN sample with no frame. Step 2, union every top 2 pair. The best pair scores 78.7 micro and 72.3 micro, first on both. Reasoning stays on for QN, off for RoboBrain. Overall, from 66.4 to 78.7. Why does this work? They rarely mix together. That is a question in 3 of the 4 quadrants, at least one model inside, about 78%. On the right, how we score misses. Sign distance to the mask normalized by its radius. Negative means hit under half a radius, near miss, beyond far miss. And the 2 models miss differently. RoboBrain misses far, median 0.9 radii, usually the wrong region. QM misses near, wide at the boundary of 0.4. When QN does miss far, it's frame confusion. In front of the mouse, the trace redesides front about 10 times and never commits. And those far misses think longer, not less. So reasoning has discrimination, not localization. That closes all 3 tasks. So the final picture, our recipe scores 83.1 overall. The best single model, RoboBrain, gets 71.7. That's a gain of 11.5 with no training. And the general VLMs collapse here, near 0 on pointing. For next steps, 4 directions are on the slide. The takeaway, no single open model wins spatial reasoning, but eliciting and combining what they already know does. That's the talk. All the analyses are online. The 2 QR codes take you to my homepage and the project page. And if you have any questions, please feel free to email me. Thank you.